Right, so for this, we're going to just look at a few practice problems related to the Chapter 19 material. So focused on entropy and Gibbs free energy, focused on determining if a system is going to become more ordered or disordered. If we're thinking about entropy, if a reaction or a process is going to be spontaneous or not, when we're looking at the Gibbs free energy change. And then with all these questions, I'm just going to kind of leave it up there for a second, maybe talk about it a little bit. But if you want a chance to work on them on your own, just pause the video and then you can kind of see the solution on the next slide, along with the setup and the explanation. But for the one we're looking at here, we want to consider a reaction where we're going to take diatomic A and diatomic B. So we've got A2 and B2, and we're going to have it in equilibrium with AB. And then we've got 2AB there just to conserve mass. And then in the, excuse me, the picture on the bottom, A is just going to be red, B is going to be blue, so the molecule AB is just going to be the combo of those two. And at equilibrium, we can see the equilibrium constant is going to be 1. So if we think about what that expression would be, we'll have K. And then on the top, we'll have products. So we'll have AB. But we'll have this concentration square. And then on the bottom, we'll have the reactants. So we'll just have A subscript 2, and then B subscript 2. So for this one, we essentially just need to make sure that because equilibrium or the constant itself is going to be equal to 1, we just need to make sure both of these pieces are the same. So when we're looking at the options here, we want to just kind of count the molecules and see what we have. And for the one on the right, number 3, we've got 1, 2, 3, 4, 5, 6, 7. We've got 7 of the products, so we'd have 7 squared if we just count the number of these atoms, or molecules rather. We'll have 7 squared on the top times 1, or divided by 1 times 1 on the bottom, because we've just got 1 of each of these diatomic molecules. So we would actually wind up with Q is equal to 49 here, because again, it's going to be 7 squared divided by 1 times 1. With the second one, now we've got just a single one of these molecules there, AB. So we would just have 1 squared on top, and then we're going to have 1, 2, 3, 4 of each of those. So we'll have 1 squared divided by 4 times 4. Really going to be 1 over 16. And then with the first one here, now we've got 3 of the A molecules, 3 of the B molecules, and then 3 of the AB. So we're going to have 3 squared on top divided by 3 times 3. So in this case, we'll see the equilibrium constant, or Q is actually just going to be equal to that equilibrium constant. So in this case, looking at the pictures here, box number 1 is going to represent equilibrium. And then we've got a couple other pieces with this one. So with Kc is equal to 1, which box represents the system at Q is less than Kc? So again, if we were to think about what that means, if Q is less than Kc, that means our system has more reactant. We're going to have more of the stuff on the bottom, which is going to be the reactant. So we're going to have more of the A2, we're going to have more of the B2 rather than AB. So for the second question here, B, we're going to be looking at box number 2. And then with letter C rather, rank the boxes increasing in order of increasing magnitude of delta G. So with that, we know this first one's at equilibrium. So the change in delta G is just going to be 0. And then with the other two, we want to think about which direction this is going to move. If it's going to move in the forward direction spontaneously, then we'll have a negative delta G. And with that case, we would be looking at the second one here. So in that case, we're going to move the reaction that way because we need to get more of the products. So we're going to see this would be a spontaneous reaction. This would be some negative delta G. Whereas this one would be a positive delta G. Because in this case, we've got too much of those reactants. So it actually works, be spontaneous in the reverse direction. We've got too much of the products, excuse me, so it'd be spontaneous in the reverse direction. All right. And then with the, oh, apparently I can't spell four right. But for each of the pairs here, choose the substance which is going to have the higher entropy. So we just want to look at each of these four different sort of questions and look at the two options we have and determine which one's going to have higher entropy. And with this, we want to remember higher temperature, larger molecules, more of the substance, more volume. All of those are going to allow for more microstates. So we're going to see a higher entropy in that case. So if we just go through these each one by one, and the first one, we've got both of these are argon. And since it's just going to be an atom of argon, we won't see rotational or vibrational movement here. So the only thing contributing to the entropy is just going to be the translational motion. And when we're looking at the gases versus the liquid, we're going to have much more disorder with the gas because those are going to be completely independent of one another. They're going to be moving around quicker. They're going to have a larger volume. So we're going to see with the first one, we should have just the argon gas. And then with the second one, in this case, we've got helium, and both of these are gases, but we've got them under different pressures. So we're going to see with the helium one, the one that's under lower pressure, if we think about it, is going to be able to expand further. So it's going to be a larger volume. We're going to have more randomness in that case, because with the 3 atmospheres of pressure, now that we got those atoms a little bit more compressed, there's going to be less space for them to kind of spread out. So there's just going to be less disorder in that case. And then the next one is kind of looking at the same thing. It's just asking it from the opposite perspective in terms of pressure and volume. But with the pressure one, we chose the lower pressure because that's going to allow that gas to expand. With the volume one, we'll do the same thing. It's just in this case, we're going to choose the larger volume because now it's just expanded further. So with 1 mole of neon, if we allow it to occupy 15 liters, rather than just 1.5, we're going to have those molecules, or the atoms, excuse me, more spread out again. They're going to be completely independent in both cases, but they're going to be more spread out. There's just going to be more disorder in that case. And then with the final one, carbon dioxide. So we could have solid carbon dioxide, which is just dry ice, or the gaseous carbon dioxide. And then with the gases, we're always going to see those are going to be higher entropy, at least for the same substance, just because they're going to be independent. They're going to be moving around freely. They're going to be more spread out. So we're just going to have more disorder in the gas phase than we will with the solid. And then with the next one, just take a moment to kind of look at these 4 different questions and determine if each of them are either true or false. And they're looking at entropy, they're looking at the laws of thermodynamics. And with the first one, delta S for an isothermal process, so that isothermal just means constant temperature. It depends on both the temperature and the amount of heat reversibly transferred. And for that one, actually, delta S is what I should have first. With it, that's going to be true because we've got this equation, trying to write reverse here. But we've got this equation for delta S for that change in entropy, where it's just going to be the heat involved in that reversible, or the reversible heat involved in that process divided by the temperature. So this one is going to be T for true. And then delta S is a state function. That's going to be true as well. And that's why we've got the equation for delta S, where we can look at the entropy of the products and just subtract it from the entropy of the reactants. It's just looking at those initial and final states. It doesn't actually matter how we get there. So because it's just interested in those 2 points, the initial and the final, the reactants and the products, doesn't matter how we get there. That's why we're going to consider delta S to be a state function. Similar to delta H as well. And then with the third one, the second law of thermodynamics says that the entropy of a system increases for all spontaneous processes. And this one's a little bit of a trick, just in terms of the wording. That's what we want to pay attention to here. So the second law of thermodynamics says that the entropy of a system increases for all spontaneous processes. And what we're going to see is the entropy of the universe will increase, but for the system, not necessarily. And with that, we can think about the Gibbs free energy equation. We can still have delta S be negative in that case, but if we've got a really large enthalpy or negative enthalpy change, delta H, so we've got G is equal to, and these should be deltas, but just so delta S. Oops, but we got this equation. We can have a negative delta S here, but we can still wind up with a negative delta G if we've got a low temperature and a large negative delta H. So for this one, it's a little bit of a trick just in terms of the wording that we need to pay attention to. But since it's referring to the system, we're going to say that this is going to be false. If it said the entropy of the universe increases for all spontaneous processes, then that would be the case. But for the system, not necessarily true. And then with the final one, the third law of thermodynamics says that the entropy of a perfect pure crystal at absolute zero increases with the mass of the crystal. And again, this one's going to be a little bit tricky in terms of what we need to focus on in terms of the wording. But since it says perfect pure crystal, we're going to have those atoms or the molecules perfectly aligned, perfectly arranged. And in that case, since it's going to be at absolute zero, we're not going to have any translational movement. We're not going to have any vibrational or rotational movement as well. So we're going to see that the entropy of that crystal is going to be zero, regardless of the mass. If we then took those crystals and started heating them up, we'd see that as the temperature increased, the entropy would be larger with larger crystals. But at absolute zero, since we don't have any of that movement, and we're referring to this as a perfect pure crystal, we're not going to have any disorder there. So we're just going to have the entropy be zero. For this one, I just underlined the first two for true. And then these bottom two we're just going to consider to be false just because of the wording there. But with this one, we can kind of use the equation we just talked about for the previous one. So we had delta S is equal to Q divided by T, excuse me. And that's what we want to use for this question. So we want to determine the entropy change when 1 mole of diatomic bromine is vaporized at 58.8 degrees Celsius. And if we think about it before we even get the calculation done, delta S, we're looking at the change in entropy. So we're looking at if it becomes more ordered or more random. And in this case, since we're going from liquid to gas, we're vaporizing the substance, we're essentially just boiling it. We're going to see that the entropy should increase, so we should wind up with a positive value here. So with a question like this, always just kind of think about what that change is. Think about what the sign for that delta S change should be. That way, when you get your final answer, you can at least kind of see if you're heading in the right direction in terms of the change there. But for this one, like I said, we're going to be using delta S is equal to Q divided by T. And for this one, Q itself is going to be the heat of vaporization. So that's just going to be Q is equal to N HV. So we've got the heat of vaporization in 29.6 kilojoules per mole. And then N is just representing the number of moles, which is just going to be 1 in this case. So that's why with the Q, it's essentially just, we don't even really need to show it, but just so you can see why the units are going to cancel. Kilojoules per mole times mole. We have mole cancel, we're just left with 29.6 kilojoules. And then with the temperature, 58.8 degrees Celsius. Remember, we just need to convert that to Kelvin. So we'll add the 273.15, giving us a Kelvin temperature of 332 Kelvin. And then we can just take those two pieces and divide them to get the change in entropy, get that delta S. And for this one, it doesn't specify an actual unit. So you could keep it in kilojoules per Kelvin, or you could convert it. Oops, I don't know why it's 0.892. That's obviously not a acceptable number. But this one should just be either 0.0892 kilojoules per Kelvin or 89.2 joules per Kelvin. But again, we see that positive number because we're making this go from a liquid to a gas. So we're going to have the entropy increase just because those molecules are going to spread out. They're going to be independent. We're going to have more randomness in that system. All right, and then with the next one, octane is a liquid hydrocarbon at room temperature that is the primary constituent in gasoline. And we want to first write a balanced chemical equation for the combustion of octane that produces carbon dioxide, gas, and then water vapor. And then we want to predict whether the delta G of this reaction is going to be more negative or less negative than delta H. But for this one, actually, so for this one, if we're thinking about the reaction, we're going to have C8H18 plus oxygen, so we'll have O2. So we'll go to carbon dioxide, whoops, plus water vapor, so H2O. And with it, we just want to make sure that we're balancing the reaction, because if we look at it now, we've got 8 carbons on the left, but only 1 on the right, so we need to put an 8 for carbon dioxide on the right. Let me just actually make these subscripts so it's a little bit easier to see what's going on. But with this, you can make a table underneath. I'm just not going to do it here because I'm not good at keeping things neat when I write with the mouse. I should have done this on the tablet instead. But we can just keep the table underneath where we're keeping track of all of those different elements on both sides. So for this one, we would need carbon, hydrogen, and oxygen. But the reason I put the 8 in front of carbon dioxide is to give us 8 of those atoms on both sides. But when we do that, now we've got 16 oxygens coming from the carbon dioxide plus a 17. So we'll ultimately need to balance the oxygen on the left as well. But since we've got O2 by itself here, I always focus on that last because we're going to be able to change the oxygen coefficient while only affecting oxygen. Whereas with all of these other substances, if we put a coefficient in front of any of these, we're going to be affecting 2 different elements. So with the next piece, I would put a 9 in front of water just to give us the 18 hydrogens on both sides. So we have H18. Now we get 2 hydrogens per water molecule. We've got 9 of those water molecules total. So we have 18 hydrogens there. Now with the final piece, we've got carbon and hydrogen balance. We can focus on this oxygen. And with it, we've got now 16 oxygens coming from carbon dioxide. We've got 9 more coming from the water. So it's going to be 25 in total. So what we would need here is 12.5. But with these coefficients, we always want them to be whole numbers. So what we can then do is just take all of these coefficients and double the entire reaction. Because if we double the entire reaction, it'll change this to 25. That'll change this to 16, change this to 18, and then we'll have a 2 in front of the octane. So it keeps everything, since we're doubling everything, it keeps it in the same ratio. But now we've got the balance there. Then just to double check it, CHO. So if we look at the carbons on the left, we've got 16 of them because we're getting 8 per molecule, and we've got 2 of those molecules. We look at the hydrogens, same idea, but in this case, we've got 18 of them per molecule, so we're going to have 36 total. And then we'll have 50 of the oxygen. And then just on the other side, do the same thing. 16 carbon dioxide gives us 16 carbons total. With the hydrogen, 2 per molecule, but we've got 18 of those water molecules. So we've got 36 on this side as well. And then with the O2 in carbon dioxide times the 16 molecules, that gives us 32. But then we're also getting oxygen from the water. We're getting 1 molecule or 1 atom of hydrogen per molecule. So we have 32 plus 18 just gives us 50. So that's going to be our balanced chemical reaction for the combustion of octane. And with this, we're going to see delta H is going to be negative. Just because this is going to be a combustion reaction, they're always going to be exothermic, so they're always going to be releasing heat. So when we think about the value for delta G, we want to think about it in terms of our, I guess, I'll do it like this. We want to think about this equation. And with it, it doesn't actually matter what delta H is here. We're just going to be comparing delta G to delta H. So we want to focus on this term. And what we need to do then is think about what the entropy change for this reaction is going to be. We need to think about if it's going to be positive or negative. And we've got carbon dioxide gas and water vapor. So we've got two gases as our products. The octane is going to be a liquid. The oxygen itself is going to be a gas. But if we think about the moles of gas, we've got 34 on the right, only 25 on the left. So we're making more gas. And then with these molecules as well, octane is a pretty big molecule, but we only have 2 of them. And it's going to be a liquid. So we're looking at the state of matter as well as how much of these substances we have. We're going to see that the entropy is going to increase. So we're going to have a positive delta S there. But since we're going to be multiplying it by the negative temperature, that's going to make this value more negative. So we should see the delta G value is going to be more negative than compared to the delta H, just because this term itself is going to wind up being negative. So with this one, we want to now look at these reactions, look kind of the same thing. Think about that equation, delta G is equal to delta H minus T delta S. And we want to think about, based on the signs of these, whether these reactions would either be spontaneous at every temperature, not spontaneous at any temperature, or spontaneous at lower temperatures but not high, or spontaneous at higher temperatures but not low. And with it, again, we're just thinking about delta G is equal to delta H minus T delta S. So if you want a chance to kind of think through it on your own, pause it, because I'm just going to show it. It's going to have the next slide that'll have all of the answers as we kind of explain it. But with it, we need to just kind of think about this equation. And if we've got a positive delta S and a negative delta H, since we're going to be multiplying the delta S by the negative temperature, that'll always give us a negative delta G. So those would always be spontaneous. The reverse then would never be spontaneous. But if we've got both of them being positive or both of them being negative, that's where it's going to be kind of dependent on what actual temperature we have that reaction at. And with the both being positive, we're going to see that those are going to be spontaneous at high temperatures, just because that high temperatures, the T delta S piece is going to be kind of the dominating factor of that equation. So it's going to take priority essentially. Whereas if they're both negative, if we want that reaction to be spontaneous, we want the delta H term to take priority. So we would want the temperature to be low so we can kind of minimize the effect of that entropy change. So if we look at this reaction here, the first one is going to be spontaneous below a certain temperature, because in this case, we've got the negative delta H, which is going to contribute to being spontaneous. But we also got a negative entropy change with delta S. So we need the temperature to be low there to kind of minimize this effect so we can maximize the delta H. And then with the second one, neither of these are working towards spontaneity. So we'll see that this reaction is never going to be spontaneous. We've got a positive delta H, so it's taking in heat, negative delta S, so it's becoming more ordered. Neither of those are going to be contributing towards spontaneity. So we'll see that this will never be spontaneous. The third one here, we've got a positive delta H, which isn't what we want for spontaneity, but we've got a positive delta S, which is what we want. So if we look at this table, we're going to see at high temperatures, because now if we've got negative T delta S and it's a really large T value, that's going to make this number much, much bigger. It'll allow it to take priority over the delta H value. So we're going to see at high temperatures, this third reaction is going to be spontaneous. And then with the final one, we've got a negative delta H, we've got a positive delta S. Both of those are what we want in terms of a spontaneous process. So we'll see that one will be spontaneous at all temperatures. And then with the next one, we've got this reaction, 2 moles of nitrogen dioxide is going to decompose into 1 mole of N2O4. And both of these substances are going to be gases. So we want to use the information below to calculate the delta G. And then we want to the standard delta G. Then we want to calculate delta G with the given partial pressures there. So remember with the little circle, that means standard. So we're just going to have concentrations of 1 essentially. So we're just going to be looking at the products minus the reactants. With the second one, we've got to take into consideration the actual amounts of those substances. So with the first one here, again, we can just do products minus reactants. And then I didn't put moles here, but what we're doing is just taking these delta G values for each of these substances and just multiplying them by how many moles we're going to have. So for the products, 98.28 kilojoules per mole, but we've only got 1 mole of that substance because of the coefficient, so it's just going to be 98.28. And then with the reactants, 51.84, but in this case, we've got 2 of those moles, so we're going to double it. We'll ultimately get negative 103 or 103.68, but we're going to be subtracting that. So we'll see that the change in free energy for this reaction is going to be negative 5.4 kilojoules. And then with the second question, we want to figure out what the Gibbs free energy change is going to be with those specific partial pressures. So we've got a slightly different equation now. We've got delta G is equal to that standard free energy change plus RT. So R is just the gas constant. And then the natural log of Q, which is just going to be essentially the equilibrium expression, but not necessarily at equilibrium. So with this one, just note that we need the units to match up. So with R, 8.314 joules per mole Kelvin. And then with the delta G for the standard reaction, we had that in kilojoules. So we just need to make sure that those match up. So we can convert this to joules, or we could convert this to kilojoules. Doesn't actually matter, but we just need to make sure that they do ultimately match. And then with the temperature, of course, need that in Kelvin. So 298, don't need to change anything about that. And then with the Q value, if we think about the reaction, products over reactants, we've got just a single mole of N2O4. So that's why we'll just use the partial pressure exactly as it is. But with the reactant now, we've got that coefficient of 2 still. So we'll square that partial pressure. So we'll have 1.6 divided by 0.4, really just giving us 10 here. And then we'll take the natural log of 10. But when we go through, delta G of the standard reaction is negative 5,400 joules. And then the RT-LNQ piece of it comes out to positive 5,704.8. So when we combine those, we get a little bit larger than negative 300. And then just paying attention to the sig figs, since we only had 2 sig figs in our pressure for the NO2, we just want 2 sig figs in our answer. So you could round this down to 300 joules, or we could convert it to negative 0.30 kilojoules. But in this case, we're going to see that the reaction is still spontaneous because we still have that negative delta G. All right, and then this will be the final one we look at, kind of using that same equation. Delta G is equal to standard delta G plus RT LNQ. But in this case, we want to figure out the equilibrium pressure of carbon dioxide in the system at 2 different temperatures. So with the first one, since it's at 25 degrees C, we can look at the delta G values for all of these substances, and again, just do products minus reactants. In this case, since it's just 1 mole of everything, we can just take all of those values exactly as they are, combine these 2 together, just add them up, and then subtract the reactant from it. And we're ultimately going to see that's going to give us a value of 208.1 kilojoules. But with this one, we're not interested in the delta G value. We're interested in the equilibrium pressure of carbon dioxide. So we're actually interested in solving for this piece. But with this equation, if we're at equilibrium, the delta G on the left is just going to be equal to 0. So we can rearrange this, just essentially subtract RT, ln, Q from both sides. And then since we're at equilibrium, Q and K are going to be the same. So that's why we just have K in the second equation at the bottom here. But now we know what delta G for the standard reaction is going to be. We know R, we know the temperature. We can solve for K. And in this case, since carbon dioxide is going to be the only substance in that equilibrium expression, that'll actually just give us the partial pressure directly. So when we look at actually plugging this one in again, delta G naught 218.1 kilojoules though, so we need to match up. That's why I just converted this to joules. I like having this in joules rather than having like 0.008314 kilojoules, but you could do that as well if you prefer. But with it, we're then going to, from this line to the next one, I just multiplied these two together and then divided. So that's how we got the negative 88. That's going to be 2,118,100 joules divided by a negative 8.314 divided by 298. And now we just got the natural log of K by itself. So if we use E, we can get rid of the natural log. So we'll just have E is equal to negative 88.0. And what we're going to see in that case is the partial pressure of carbon dioxide is going to be an extremely small number. It's going to be 6.0 times 10 to the negative 39th atmospheres. And then with the second one, we've got to do a slightly different process. So in this one, we're looking at 1100 Kelvin. So for this one, what we're going to do is use the Gibbs free energy equation. G is equal to H delta, or delta G is equal to delta H minus T delta S. So for this one, we've got those two values. We can again do products minus reactants to figure out what the enthalpy change of this reaction is going to be. We can do the same thing to figure out what the entropy change is going to be. So with these two numbers down here, 269.3 for the delta H is just taking these two numbers, adding them together, and then subtracting the reactant from it. And then the delta S is doing the same thing. It's just in this case, we're looking at the second row of numbers here. And these just come from the textbook. So with a question like this on a quiz or test, you would need to be provided with this answer. There's no way you'd be expected to memorize these or be able to just like calculate them without just having this information provided. But we can use that to get the delta H and the delta S we see here. And again, we want to just pay attention to the units, because with delta S, these values were in joule per mole Kelvin, whereas the delta H was kilojoules per mole. So we just need those to match up. And in this case, I'm actually going to convert joules to kilojoules. So that's why we've got the much smaller number here. But with the Gibbs free energy equation, delta H minus T delta S, that's going to allow us to calculate this value for the reaction. And we'll just plug in 269.3 for delta H, 1100 Kelvin for T, and then the 0.1719 kilojoules per Kelvin for delta S, because again, we changed the unit to match up with delta H. And what that's going to give us is a standard free energy change of 80.21 kilojoules. So now we can take this value, go back to the equation we just used for the previous one, negative RT ln K, because again, we're looking at the equilibrium pressure. So when we have this reaction, it's going to be the same sort of process in terms of solving it as the final one was now. It's just we've got a different delta G value on the left. We've got a different temperature in this case. So that's why we just see a different number here rather than negative 88. We get negative 8.77. But we can again get rid of that natural log by using E. And then the K value, which is still just going to be only including carbon dioxide, because both of these solids don't get included in the equilibrium expression. We're going to see in this case, the pressure is going to be much, much larger. We're going to see it's going to be 1.6 times 10 to the negative 4th atmospheres. But with this, if you do have any questions on any of this, or if you look at the practice problems on Canvas, anything in the textbook that you have questions about, please let me know, and we can look at those either in class or get together during office hours or something.